Today we'll build the gradient descent for a complex function. It's not that easy as it was for the 2D parabola. We need to construct a more complicated method. Momentum, a powerful method to solve this challenge. The gradient is a vector of partial derivatives of a function. Essentially, it's the derivative of a function with respect to all its variables, represented as a vector. Let's revisit the concept of the gradient for a moment. For example, if we have a function f of x and y, then the gradient of this function is a vector of its partial derivatives with respect to x and with respect to y. The gradient is a multidimensional version of derivative. We know that the derivative represents the steepest ascent of a function, or the rate of change of a function at a given point. You can check my post why is the gradient is the steepest ascent, but long story short, this expression calculates the rate of change of a function over a small interval h. We change the input of the function f, subtract the function f with the original input over this infinitesimally small value h, because we have limit when h goes to 0. At any point x, the derivative indicates the slope of the function, or the slope of the tangent line to a given point, showing how f of x changes most rapidly with respect to x. And same logic we have for the gradient, but with respect to all of the variables of multivariable function f. On a gradient field plot, you see the gradient vector at each point of a 3D function surface. The gradient vector point in the direction of the steepest ascent. If we start at some point and follow the gradient direction, we go straight to the infinity with this 3D paraboloid, yeah, because we have no any maxima, but we go to the direction of the steepest ascent of a function. If we follow the opposite direction, it means that we go straight downhill to the minima of this function. This is the idea of the gradient descent. Follow the negative direction of the gradient to reach the function's minima. For this gradient field, we used 3D paraboloid function, gradient of the function, and then we built the surface, and after we built the gradient field. You can play with this code. You can find the link under the video to this Jupyter notebook. In this visualization, you can change the grid density or arrow scale, yeah, or just play with this code as you want it. The most intuitive way to understand the gradient descent is by reducing everything to the 2D case. Input x and output y. You can check my previous video where we just build the gradient descent into D. So you can see we use the central difference approximation of the derivative, or the numerical difference. I have a video about this, you can check how it works. And we have this gradient descent and the core of this algorithm inside this loop. We use center difference approximation to compute the gradient, yeah, or just compute the derivative. But basic idea of the derivative is just 1D version of the gradient vector, yeah. Then we update the x coordinate in the opposite direction of the gradient, yeah. You can see that we subtract from our initial coordinate the gradient times the learning rate. We move in the opposite direction of the gradient with this rate of change that we call learning rate, and build this pass, yeah, we just append to our result array next coordinate and move forward. So it looks like this finally, yeah. Let's just run it again, yeah, and you can see that we have starting x point, yeah, we can change the starting point. Let's say from 10 to -10. We can play with the learning rate. If the learning rate is too high, we just starting to bouncing around this minima point, and we can change the number of iteration, yeah. You can play with this simulation by your own, and you can find this code under this video. For a 3D gradient, the concept is similar but scaled to multi-dimensional space. The gradient represents the direction of the steepest ascent of a multivariable function in every dimension. And if we follow the negative direction of the gradient, we create a gradient descent in multiple dimensions. First, I want to use a hyperparabola. It's the easiest way to start our gradient descent journey. The slope of the function is smooth, and the minimum of the function is pretty clear for the gradient descent. Just follow the negative gradient to reach the bottom of the ball. Our 3D paraboloid function has two parameters, x and y, and we sum the square of these parameters. This function represents a simple 3D paraboloid, which is essentially a ball-shaped surface, where the height of the function increases quadratically in both x and y directions. And the gradient of the 3D paraboloid function is partial derivatives with respect to x and partial derivatives with respect to y, and it equals 2x and 2y. It's a vector with two terms, and the gradient points radially outward from the origin, since the function increases in the direction from the center. Quadratic shape of the paraboloid looks like a ball. Let's define a function paraboloid, and we have one parameter vector x for this paraboloid, and we know that we have two items in this vector, x and y. So then we need to return a squared version of every term, and we need to sum them up, yeah. So we sum up x squared and y squared, yeah. But let's just think for a moment, yeah. This is the definition of the dot product, yeah. If we just multiply vector x by vector x, we must multiply every corresponding item and then sum them up. And I believe if we just use this version, let's create a function paraboloid 2, and we return x dot product with x, it will be absolutely the same result. Let's check how it works. We need to create an input vector x, and it's numpy.array. Let's use two terms, 2 and 3, and then let's call the paraboloid with this vector x and paraboloid 2 with the same vector x. And it's absolutely the same result. There is no surprise, yeah, because that's exactly the same as just dot product between vector and same vector, yeah. Okay, let's use this version because I like it more, yeah, than this one. And let's mark that we use for this vector x numpy array. Okay, good. Then let's program the gradient of this 3D paraboloid. Let's define a function paraboloid gradient. We receive the same input with the same data type numpy and the array, and we need to return numpy. Okay, let's follow the same logic, yeah? We have two items in this vector x, and then we need to return 2 times the first coordinate x and 2 times the second coordinate y. And we can wrap it by the numpy dot array. Okay, and it looks like this. But if we just multiply this vector x times 2, it will be absolutely the same result. Yeah, we just multiply every corresponding item in this vector x. Let's create a function paraboloid gradient 2, and I just return 2 times this x. And let's compare the result. We just take the same vector x and then run it for the paraboloid gradient and for the paraboloid gradient 2. Let's check the result, and no surprise. There is no surprise. Yeah, it's absolutely the same result. Okay, great. I prefer this function paraboloid gradient. And now let's define a function gradient descent, but for the 3D. We know that we need to have a start coordinates. Let's just use start coordinates as the numpy array. Also, we have the learning rate, and the number of iterations. Learning rate, we mark it as the float data type, and number of iterations, it's an integer. We need to build the whole path of the gradient descent, yeah, just for the visualization. So let's create a function path, variable path, yeah, as a list, and we put this start to this list as the initial point. Okay, then we need to create a loop, and we know that we need to make this number of iterations. So let's create a range with this number of iterations. Now let's create a variable gradient right over here, and we know that we have this paraboloid gradient, and we can put start coordinates right over here, and it computes for us the gradient. And as far as I remember, the gradient descent just followed the negative direction of the gradient. It means that we need to subtract from the start coordinate our gradient times this learning rate, yeah, because we follow the negative direction of the gradient with this rate of change, with this parameter learning rate. And for the next step, we need to append to our path the new coordinate, yeah, that we compute right over here. And as the last step, let's just return numpy dot array, and we wrap this path to the numpy dot array. Yeah, we just convert list to the numpy array, meaning that we return right over here just numpy array. And let's add this return type to the paraboloid and paraboloid gradient, yeah, because we return just numpy array. We have numpy array in the input of this function and in the output. And now let's build the surface that visualize this paraboloid and the gradient descent path. Okay, and here we go. We just built the lean space mesh grid for this lean space, and convert mesh grid into 2D array and put it as the parameter to our paraboloid function. Then we build the gradient descent path. We have this start vector coordinates. Yeah, let's rename it to start. We have this learning rate and number of iterations. Learning rate 0.1 and number of iterations equals 10. So then we just plot our surface. Yeah, we have x, y, and z coordinates. Then we right over here on the we first of all just create a pass on our surface, on the 3D plot of this ball, and add the surface on 2D contour plot right over here. So let's run this code. Looks like we have a trouble with this matrix multiplication operator. Okay, and long story short, let's replace this dot product, to the square and some operation with x equals 1. I think that it will work without any problems. Okay, and here we go. Right now we have this 3D gradient descent visualization and 2D contour plot with the gradient descent pass. We can see clearly how it works. But probably we need to add some interactive elements, to play with the learning rate and with the number of steps. Okay, I add this function plot gradient descent, wrap everything by this function. Here I have just start coordinate. I just put right over here start x and start y from our interact function. Let's run this code. And here we go. Right now we can change the start x coordinate or start y coordinate, like this. Also we can play with the learning rate. We can make it more, and as far as I remember from the 2D version, if our learning rate is too high, we're starting to bouncing around the minima. Let's choose this one, and I can see how it works. Just let's move to the left top corner, and you can see clearly, it's just bouncing around the minima. If we increase the number of iteration, it looks like this. So it's very similar behavior with the 2D version of the parabola. You can play with this interactive plot by your own, and I don't want to go deeply how this 3D visualization works. You can check it by your own. You can find this code under the video. The most important information, it's right over here. It's this gradient descent 3D function. And as far as I remember, we just built the whole gradient pass. But for the real gradient descent, we don't need the whole pass. We just need one last point. Just only the minimum of the function. Okay, and let's reduce the learning rate to, let's say, 0.1 and number of iteration to, let's say, 10, or a little bit more than 10, let's say 20, and right now you can see that we clearly point to the minima of our function. We reach the bottom of our ball of this 3D paraboloid function. It works very fast and find the minimum without any problems. We just have this half parabola trajectory, straight to the minimum. But this isn't always the case. For complicated function shapes, there is no easy and straight way to find the location of the global minima. And in many cases, gradient descent just can fail into a local minimum, give us a suboptimal solution rather than the real optimum of a function. I can show you one more example.